Okay, hello. I am going to explain how to do problem 1 of the free response that was worth 16 points. And yeah, I'm going to explain how to do it. And I'm going to go through all the steps. So, to start with, I'm going to draw the picture because I think it's helpful. As I draw it, it helps me understand more what's happening. So, the question is, a flat disk of radius r has a uniformly distributed charge q naught, and a thin radius of radius small r, and a thickness dr is shown in the figure inside of the other disk. So, this is our ring, and it has a thickness of d small r, and this is a small r radius. And then we have this larger big R radius. And here we have the x-axis, and let's say this is x. And then we want to find, and this is the distance between the ring, the edge of this ring, and a point on the x-axis. And this distance is going to be equal to x squared plus r squared, because if you do the Pythagorean theorem, then you have x squared plus r squared equals this length squared, whatever this length is, so that would just be equal to this, is equal to that distance, right, between some r and the x-axis. So we know that q naught is uniformly distributed over the disk, and now let's pull together some formulas that we know that are going to be useful to answer this question. So we know that the voltage is equal to K times the integral of dq over a distance, which is usually r, but in this case it's the distance. It's not r because r is something else, so it's going to be this distance. And then we know that dv is going to be just the derivative of this side. You have to take the derivative of both sides if you're going to do that. So we have k is equal to we have dv is equal to k times dq over this distance, and that's going to be how we find dv, and then k is equal to 1 over 4 pi e naught. So, to start with, let's go to the charge density, because that's what we used to do in class when we were doing these problems. Charge density is usually going to be the charge over the area or the volume, depending on what we're using, right? So in this case, we're going to be using the charge density of the ring because the question asks calculate the infinitesimal point potential dV along the x-axis due to the ring. So we're going to be using the ring. And yeah, and so the charge density of the ring is the charge over the area of the ring, or the volume of the ring. So that's going to be dq naught over, that's the charge, over 2 pi r dr. So the reason why this is the volume is because 2 pi r is the circumference times dr, which is the thickness, is going to be equal to the volume of the ring. So we just need to plug these equations in. We need to plug in this and plug in this to get into this formula, which we understood from this formula, to get the answer to this question. So we have dV is equal to K times, and then we cross multiply these two, right, to get what dq naught is, and to put our expression in terms of dr instead of dq naught. And then we get Q, charge density, 2 pi r over this square root x squared plus r squared dr. So this is what we have for our dV. I'm going to leave it like this. And this is the answer for this is part A. Part B asks us to find the potential V along the x-axis due to the entire disk. So we're just going to find the derivative of dV, right? Because the derivative the integral of dv, which is going to be v, right? That's basic calculus. So what we're going to do is we're going to take the integral of this. So we have dv is equal to the integral of k charge density 2 pi r over the square root of x squared plus r squared dr, and the boundaries, let's put in the boundaries now just so that we know what we're doing. The boundaries are going to be 0 to big R, right? Because this is where we're coming from, and then the furthest we can go out is this larger R, right? Because it's just asking due to the entire disk, so it wants us to put those limits in. So what we're going to do is pull out all the constants. So we have, sorry, I don't know why I wrote dv. This is just v, because we're taking the integral of this. So we're going to pull out the constants. We have k, and then we have the charge density, which is constant because the charge is uniform, and 2 pi, pull out, and now we have this integral. Keep everything that we can't pull out, that changes inside the integral. So yes, so yeah. Then we need to figure out how to get this integral. So what this is a simple u substitution. So u substitution, right? So we're going to make u equal to x squared plus r squared, and du is going to be equal to 2r, because the derivative of this with respect to x is equal to, with respect to r, is equal to 2r, because this is a constant, and this is because we're not taking it with respect to x, we're taking it with respect to r because that's what's changing in our expression. So the derivative will be 2r, and then, so if we want to find what r is, we just go like that, and we get du over 2. So we can plug this into our formula, and we have k charge density 2 pi, and then we're going to have our integral sign, and then we're going to have du over 2 instead of r, and then u again, because the square root of u actually, because because this is u, so it's the square root of u, du over 2. That uses up all of our, we substituted everything correctly. And now we're going to pull out the constants, right? So pull out the 2, which crosses these 2's out. So we have k, charge density, pi, integral of du over the square root of u, which is really equal to k pi, charge density pi, and then u to the negative a half du. So we can do like the exponent rule, and then we have to just add 1 and then put this over that added number. So we get k charge density pi u to the a half over 1/2, which is actually going to be 2k charge density pi square root u, right? And then let's place our stuff back in. So let's substitute back from u. So we get um, 2k charge density pi times then the square root of u, right? Which is really the square root of x squared plus r squared. And then we still have to evaluate this at our boundary points, which were 0 and r. So, oh sorry, I didn't mean to make this a big R, that's still a small r. And we'll have to replace that with a big R when we want to do our boundaries. So we get that the voltage is equal to K2 pi charge density times the square root of x squared plus big R squared, because we put that in now, minus square root of x squared, because when r squared is 0, r is 0, and you just have square root of x squared here. So this is what our voltage is going to look like. Okay. So, C. Our next question is, what is the potential in the limit when r over x is much, much less than 1, i.e. very far away? Is this the expected result? You may use the approximations at the end of the reference sheet. So, when r over x is much, much less than 1, so that x is approaching infinity, and it's very, very far, what we want to do is manipulate our formula that we have for v of x, and pull things out in such a way that when we use an approximation that we can only use when this is holds, this special case approximation, then we can prove something really meaningful about this type of situation that we're being presented with here. So, we know the approximation is that we're going to be using is the square root of 1 plus x is square root of 1 plus x is roughly equal to 1 plus x over 2 for any x that is much, much less than 1, right? So, let's figure out what we're going to do here. So this is not the same x, this is just like the vague standard notation of it, but we're talking about different x's here. We're going to use actually r over x for rx, because that's what we have here. X is less than 1, so this entire thing is much, much, much less than 1. So r over x is much, much less than 1. So let's try to massage the formula so that we can get this into our formula. So v of x is equal to 2 pi charge density k, and I'm just rewriting it because we're going to be reusing it, x squared plus r squared minus, this is really going to simplify down to x, so you can adjust that over here. Sorry that I didn't do that before. It's really going to be the absolute value of x, because this is really equal to negative or positive x. So we have this, right? And then what we want to do is we want to try to get one of these characters to be a 1, and one of them to be an r over x, or a r squared over x squared, or something to that effect, so that we can use this approximation and replace it into our formula. So, the way that we're going to do that is keep the constants the same, and then we're going to replace what we have here with another notation that means the same thing, which is pull out an x squared, right? So we can do that, and then we can get a 1 plus r squared over x squared, we pulled that out, from just this side. And then, actually, we're pulling out a square root x squared, so that's really pulling out an x. So if we pull that out, we get 1 from here, because this times this is going to be the same thing as that. These are the same. So, and this is really just x, so we're pulling out an x, which means that we get a 1 over here, and we have to pull out an x squared from here too, squared x squared. So this is the type of situation, this is the kind of formula we get from that. So that means that now we can use our approximation, and we have to attach this over here, pull this out, and what we have is 2 pi charge density x, okay, and then we have this over here, which looks a lot like this over here, so now we can substitute. So we have 1 plus x over 2, so that's r squared over 2x squared, right? Because r squared over x squared over 2 is going to be r squared over 2x squared. And then minus 1, bring that down from here, right? And so now we can see that these 1's are going to cross out, and these 2's are going to cross out. So we're going to have pi charge density kx r squared. Sorry, I'm just in the middle. R squared over x squared. But we forgot to cross out this, so cross that out. And then we have k charge density pi r squared over x. Okay, and this is what we are left with. So we know that Q naught is going to be equal to the charge density times pi r squared, right, for the area of a disk. That's what the charge density is. So let's replace that back in just so that we can see our results more clearly, because that's what we have right over here. So we have Q naught k over x. Sorry, this was technically an absolute value of x because it's an x squared. Doesn't really matter. And if you look at this expression that we have here, this is the formula of v of x for a point charge. So this is what we're left with, right? For this type of situation where r over x is much, much less than 1. And x is very far away, it's approaching infinity. It's very, very far from this disk. You would expect that the disk is going to look like a point charge because the area is going to be so small compared with how far away you are, right? And this is what a point charge is, because a point charge is Q naught times over 4 pi E naught R. That's the formula for the voltage of a point charge, and that's what K. You can substitute 1 over this for K, and then you have the R is X in our case. So if you look at this, that's actually the same formula, and that makes a lot of sense. And if you replace, if you make x go to infinity, this is going to go to infinity much faster than this. So this whole expression would go to 0 if you make x go to infinity. And eventually there would be no more, everything would just go to 0 and cancel because it was so far away. It would no longer be substantial. So, okay. Then we have the next question. Use your result from part B to find an expression for the electric field along the x-axis. Okay, so I'm actually going to go on a new page for this. So, make sure that you can still see it. We're going to still use this expression, so I'm going to keep this in it. So, let's use our expression. So we have v of x is equal to k 2 pi charge density x squared plus r squared minus x, right? And that is what we have we're going to use that. Okay, so we want to find the electric field, and we know that the electric field is actually equal to the gradient of the voltage, right? But we only need to find this for Ex. And so it's much simpler since we only have to do this over Ex and not Y and Z, because the question asks, use your result to find the electric field along the x-axis. So what we're going to do is we're going to take some partial derivatives. So we know that Ex is equal to negative the derivative of V over the with respect to x, right? So this is what it means when you're taking the gradient of something with respect to a partial derivative with respect to x of v, which is really equal to negative the partial derivative of x, and then of the function v of x. So we're going to use this again, and we're going to substitute, what I meant is we're going to substitute v of x. So we're going to put in our v of x from here, k 2 pi square root x squared plus r squared minus x. And now we're going to take the partial derivative with respect to x in this statement, in this equation. So we get negative 2 pi, these are constants, times a half x squared plus r squared to the negative a half times 2x minus 1. Okay, so the reason that what we did here was we used the exponent rule to we know this whole thing times a half, so so we had to add 1, we had to subtract 1 and then pull that to the other side, so we multiply this by a half, subtracted 1, got negative a half, and then it's the product rule, it's the chain rule, there's a function within this function, so we had to deal with x squared, which the derivative of is 2x, so this was the product of the chain rule. And then minus 1 because the derivative of x is going to be 1. So this is how we found that. So then if we keep going with this, let's just write this in a better notation. We get x, we get that this equals to negative 2 pi times our charge density and our k. And then we have x over square root of x squared plus r squared minus 1, because we had a half over here, but then we had a 2, right? So there's a 2 underneath and a 2 on top, and those canceled out. So this is what we ended up with. And then, yeah, and then if we want to just write this a little bit better, we've got ex is equal to, let's pull this negative out and put make this, let's just move it over here. So then we get 2 pi k, charge density k, 1 minus x squared, not squared, sorry, x over x squared plus r squared. And this is going to be our final answer to what the electric field will look like in this situation. So that's good. So that is how you find the electric field from the voltage. You just take the gradient, but it's only going to be one partial derivative for us, not the whole gradient, because we're only doing the x component of the electric field, because that's the only one that's relevant here. Okay, next we have to do E. So the next question is, what is the electric field in a limit when x over r is much, much less than 1, i.e. very close? Is this the expected result? So we're going to use another linear approximation. X over r is much, much less than 1, very close, right? So this means, so this is kind of complicated. Actually, let's do it on a new page, because I don't want to run out of space and then have to change the page in the middle. So so x over r, so this is E, x over r is much, much less than 1, very close. Basically, x is approaching 0, r is approaching infinity, and that is what is happening. Okay, so we know that Ex, we're going to use the formula for Ex, because we're trying to find the electric field in limit in this situation. So we're going to use Ex. 2 pi charge density k 1 minus x over square root x squared plus r squared. So we're going to use the approximation that we used before, same one, and I'm going to write it again. Actually, we're using a different approximation from the one that we used before. I think. Let me check which one we used before quickly. Yeah, we're using a different one. So we're using our other one that was on the sheet, on our reference sheet. So this is 1 plus x. 1 over 1 plus x is roughly 1 minus x over 2. Last time it was 1 plus square root of 1 plus x, not 1 over, but just plain square root, is roughly 1 plus x over 2. So this is for x's that are much, much less than 1. And for us, we're going to use x over r for x, because x over r is much, much less than 1 for us, right? So let's keep this in mind. And then let's go. Okay, so again, we're going to try to massage this equation so that we can plug this in and then use it to show something meaningful about the electric field in this situation, where x is approaching 0 and very, very close to the disk. Basically, the point that you're choosing is really, really, really close to the disk. So let's try to massage this equation. So we have, what we're going to do is we're going to try to pull out an r, or a square root of r squared, in order to get 1 plus some x, because then we'll have a 1. And x is going to be x squared over r squared. So I'll show you. 2 pi charge density k 1 minus, and then we have x over square root of r squared times square root of x squared over r squared, because if we pull that out we have to put it underneath, and then this is going to be a 1, right? So that's what we have. So this is actually just going to cancel out to an r, and we have here now this substitution, right? So let's go again. Let's start this again. Write this again, sorry. 2 pi charge density k 1 minus, and now let's just replace this with x over r times x over x squared plus over r squared plus 1, right? And then we can replace this because, sorry, we're going to pull out an x and make this, and then this would become a 1. I'm sorry. So we pulled out an x from this whole formula, and then we got x over r times 1 over x squared plus 1. So that's how we did that. Yeah. So we pulled that out, and then now we have we can replace that with our linear approximation. So we have, I mean, not with our, just with our approximation. I don't know if it's linear or not. So we have 1 minus x over r times 1 minus, and then our x over r is, we're calling it x squared over r here. So it's going to be 1 minus x squared over r. Sorry, I don't know why I think I wrote last time r over x, but really we're using x squared over r squared for that. And you can still use it because if x over r is much, much less than 1, then x squared over r squared is also going to be much, much less than 1. Last time we used r squared over x squared instead of r over x, because r squared over x squared, if it's less than 1, also will be. So like they follow the same suit. Yeah, and then it'll be divided by 2, because x over 2, x squared over r squared, divided by 2, divided by, but divided by 2, so that's what you're going to get. So, yeah, so let's simplify this expression, and you get 2 pi charge density k 1 minus x over r. Just let's distribute this because we pulled it out before, so distribute it back in, minus x to to the third over 2r to the third slash cubed. And we know that xr goes to 0, right? These both go to 0. Why? Because it's much, much, much less than 1, right? X is much, much less than 1. R is approaching infinity. So both of these characters are going to go to 0. Both of these expressions are both going to go to 0 because they're so, so, so small and you're approaching 0. So what we're left with is e over x is equal to 2 pi charge density k, right? So this is what we're left over with. Now this is actually just equal to what is important about this expression is what we're trying to understand from this problem is that, first of all, this is independent of x, right? Because you're so close that x no longer matters. Why? Because this is actually the formula for the expression of the electric field in an infinite plane. So that's what's really interesting about this equation, because if you're so, so, so close to the disk, then the disk looks infinite because you're infinitely approaching it. So like the size of it no longer matters. X doesn't matter any longer. R doesn't matter any longer. It doesn't matter how big the disk is. It doesn't matter how close you are to it. It's infinite, and you're infinitely approaching it. You're going closer and closer to 0. So the formula, so x no longer matters, and the formula matches that of E in an infinite plane. Okay. So next, last part